Assalamu alaikum, students. This is lecture number 12 for electric machinery fundamentals. Today we have some very small topics, and we will be having a transition from one chapter to the other also. In fact, in the lab, you have started working, and in fact, you will be almost at the end of your 8 experiments, which you have been doing before your midterm exams. So this lecture is covering a lot variety of topics, and today we'll be most probably focusing ourselves mostly on the shunt and separately excited motor and its characteristics, and hopefully the next lecture would be related to the characteristics over there, and in the next 2 or 3 lectures we will sum this all up, and the DC machines portion would be complete. Okay, so today's content, as you can see over here, are the yoke effect, because this is very important. We have discussed this previously also, but I'm going to discuss it again over here. Then I have the power flow diagrams. Then very important thing which normally many engineers ignore it for a DC machine is the brush voltage drop, the efficiency of a DC machines, what are losses taking place. We will discuss them just briefly, and then at the end, and as I told you, we will be talking about the shunt and the separately excited motors. So moving ahead with this one, as you can see over here, that I have drawn a cross-sectional view of a DC machine and named them over here, the parts over there as yoke, the rotor. The whole of this one is actually called as the stator. The carbon brushes are not shown here for obvious reasons, because the commutator is not here shown. Then I have shown you the slot, the armature, on this one, the armature windings, and then I have the field windings, the poles over there, and you can see over here I have put the windings also here over there. This winding which is done on the pole, certainly this is called as the field winding over here. And I guess I don't need to actually tell on this one that the current which is actually going to flow in this winding is actually going to be IF, which is going to be field current, and the current which is going to flow inside any of these ones is certainly going to be called as the armature current over here, because you have been doing experiments in the lab. So I guess this is totally just repetition of what you have been doing over there, and we have talked on this one. Now the question over here, before why this topic is again being discussed, is actually the eddy currents over here. Now eddy currents, as we all know, as I told you in the transformer case when we were talking about the transformer excitation from an AC source, that eddy currents are always going to be produced, these eddy currents, whenever there is going to be a rate of change of flux. Now, if your flux is not changing, then there is no way that eddy currents can actually be produced. So over here in a DC machine, when I'm talking about a DC machine, certainly as the name speaks out, it's a DC machine. So there is no actually change in flux over there. But normally, whenever in the industry there is a DC machine being used over there, this source over here is a DC source. But whenever you want to change the speed of his DC machine, you have 2 or 3 different methods over there, and we will be discussing them in the next lecture, speed control. But since we have done experiment in the lab that is related to your armature voltage control and the field winding control and all that stuff over there, so those supplies over there which are controlled actually, which are controlling the applied voltage to the field winding or the armature winding, they are PWM based, or they are based on some semiconductor switches, maybe a transistor, MOSFET, or something like that. So what this means over here, that this field current, or maybe this even armature current which is being supplied, this can be a little discontinuous. By discontinuous, I mean that the winding current, technically we want that it should be a straight line like this, but practically it's not going to be a straight line. If I can show this one, so maybe it is going to be a series of PWM pulses like this, and this means that there is a change over there. So the average value of this all will be something like this over there. So the motor is actually going to work at that average value of this one value over there, but technically you are being provided over here with this PWM pulses over there, either on the field winding or on the armature. Now technically speaking, when you are having this frequency being applied, and that is a PWM shape current or the voltage applied over there, then certainly this means that there is going to be a rate of change of flux. So this means eddy currents are always going to be provided. Now rotor, it's already, we know that it's always going to have an AC current induced in it, and because of the commutator action, this is going to be converted into DC. and then it's going to run on. So technically, eddy currents are always present inside the armature. So armature is always going to be laminated. Why? Because it is going to have an AC current induced inside it, either if it's a motor or it's a generator, both cases. So eddy currents are always going to be there. So this lamination for the rotor is a must always. As far as the field winding is concerned, if certainly it is a permanent magnet, then certainly there is no need of any laminations over there, because eddy currents are not going to be there, because magnetism is going to be constant from that machine unless and until it veers down and the magnet loses its magnetism. But otherwise, if you are working it on a DC supply, and that DC supply is going to give you something like this, a discontinuous current waveform, or maybe the current is changing, or maybe even if this is a simple DC variable supply and you are changing the DC supply, then there are going to be eddy currents produced. And because of those eddy currents produced, this over here, the poles, they are going to be made up of laminations. So the poles are going to be made up of laminations. Now, if you are a good manufacturer and your machine is going to be subjected to a lot of variations in the field current, and since yoke over here is this portion of the machine which is actually completing the flux path. So if I have a north pole over here and a south pole over here, then this certainly means that the flux lines are actually going to flow from this north to south, and half of them are going to complete their path here, the half of them are going to complete their path here. So this flux inside the yoke is also going to be a little discontinuous, and whenever it's going to be a little discontinuous, eddy currents are always going to be formed over there. So this is very important that your yoke can also be laminated. But again, this depends upon the manufacturer also. Normally they make the pole as actually the most important, because here the discontinuous current will be flowing over here in the field windings, and it will then have that discontinuous field flux over there, and that field flux, since it's going to have a rate of change of flux, so there is going to be an EMF induced inside this, so there is going to be eddy currents flowing over there. So you are going to have the poles also laminated. But for good manufacturers, they will make the yoke also as the laminated case. But again, it's again a manufacturing trade, whatever you want to actually go on with this. So eddy currents, wherever they are produced, you have to make it laminated over there. So this is the first topic, and there is one more topic which is a very much importance, and this is going to be very interesting for you also. Now, you all are familiar with this thing that whenever there is going to be a pole north and south, and then there is going to be an armature, it's very simple armature, nothing, no slots, nothing is shown over there. But in the last topic we discussed armature reaction, and over here, if you remember, if the armature reaction was take place over there, then the whole phi f was going to be concentrated on this region over there. So what happens, the field flux lines, they actually try to feed over here in this corner edge over there. Now when this is taking place, this is going to have a saturation of flux over there, and certainly there is going to be less flux in this region. So overall what happened, the overall net flux of the machine was going to go down, and certainly if it's going to be a motor, then it's going to have a less amount of torque, and if it's going to be a generator, then it's going to have a less EMF output from here. Now there is one technique which can be done in the construction of the machine, which is shown over there, which is called as the chamfering of poles. Now you can see over here that this portion has almost a constant air gap. This portion, similarly this portion over here. But as soon as we move here and these four regions, the air gap has been actually a little increased over there. Now what will this do? Now we all know that what the conductor which is going to be here in this region, then certainly they are going to have a less EMF induced, because certainly more reluctance mean that less flux is actually going to reach that area. But this small air gap increase over here is actually going to make less lines having a concentration over here, if I can show that. So less lines concentration would be here. I don't say that the armature reaction won't be taking place. It will still be taking, but less concentration in this region and in this region. So the overall net flux, it will still decrease, but not by the same amount as it will be happening in this range over there. It will be smaller in this picture. So this chamfering of poles is actually done so that the magnetic axis, which is actually going going to tilt over here, if this is tilted over here in this direction, then this will be a little less tilted over there. Why? Because less concentration of flux lines are there than otherwise. There will be still flux lines flowing over here like this and some flux lines flowing over here like this. So certainly there is going to be some less deficit from the net flux decrease over there. So this technique of chamfering of poles is also done in AC machines. We will discuss that one for the pole shape or the waveform shape of the AC generators when the time comes after your midterms, when we are discussing AC machines and AC generators in very much depth. So this chamfering of poles is also a very important technique. In fact, in this diagram which I showed you just now in the last slide, this one I have shown this chamfering again over here like this and this air gap is different and this air gap is same over there. Otherwise this one, this air gap, this air gap. Technically, yes, there will be a loss of flux over there, but armature reaction, since we know it's going to be a very detrimental thing and it's going to have a lot amount of problems for us. So technically, this chamfering of poles is going to be a very good thing for the machines, especially those machines which are going to be subjected to a lot amount of armature reaction. Now over here, coming on to the losses in the machine, as we all know, it's a machine, it's not a 100% effective machine, it has losses. And I have told you previously also that DC machines, the maximum efficiency that you can go in these machines is not more than 60 to 70%. Maybe in some rare cases it can go to 75% whenever you have those compensating windings, interpoles and all that affects being remedified over there, then certainly your efficiency. But our lab machines on which you are doing your experiments are only limited to 60 to 70% over here. Now coming to the losses in the machine, we all know there is copper inside it. And where is that copper? Copper is inside the windings. There are two windings inside your machine. One winding is actually this field winding over here that we have called over here. The other one is called as the armature winding as indicated, and certainly it is done on the armature or the rotor, this rotor over there, or the armature. So these two windings, they are going to be, one is the armature winding losses, other one is going to be the field winding losses. And you all know the formula for the resistance based losses, which are I square R. So you can see this is the armature winding loss and this is the field winding loss over there based on their current which are flowing over there. Now these are equally applicable for your shunt machines. Over here, the shunt machine armature winding, the shunt machine field winding. But overall, when I'm talking about the shunt series field winding, I guess you are already familiar with this, that the current which is flowing inside a series field winding is called as IA or ID, totally dependent upon which variable you are using. So for a series machine, these losses are actually going to be called as IA square RD. So these are for your series machine if I'm talking about, because in series machine, the field winding is in series with the armature. So that's why IA square RD or ID square RD, whatever nomenclature you have been using in the lab, IA or ID, same thing applies over here. But if you have a shunt machine or maybe a separately excited machine, then these two are applicable over there. But if you have a series machine over here, then certainly you have IA or ID current flowing series, everything is in series. So the series field winding current or losses are IA square RD over there. The next thing to actually come into contact is actually the brush loss, as you can see over there. This brush loss is going to be the losses inside that carbon or graphite carbon brush which you are actually going to be. It can be, you all know graphite is a allotrope of carbon, so either it's going to be just simple graphite or graphite plus some carbon added over there. So it's always going to have some resistance developed over there. Yes, it's a good conductor for electricity, but still, because of the sparking, the inherent sparking due to LDI by DT effect and all other thing, it is going to have a voltage drop. This voltage drop is very significant if the load current is certainly large. So this VBD is actually going to be the brush voltage drop over there, and certainly there is going to be a current flowing through those carbon brushes. That current is actually going to be the whole current in the machine. So there is always a brush loss which we call as P with BD as subscript over there. So PBD is equal to VBD into IA. So this is the brush loss over there, again dependent upon the brush voltage, and certainly this is taken as constant, but you can't say it because as the speed of the machine changes, this brush voltage drop is going to change. Certainly, because if the machine is running at a low speed, then the brush voltage drop is different. But technically, this thing varies from machine to machine, and certainly depending upon the commutator on which those carbon brushes are actually sliding. In practical, the carbon brushes, when they are sliding on the commutator segment, the point we actually want to erode is actually the carbon brushes. We don't want to erode the commutator segment, because the commutator segments, they are made so much thick that during the lifetime of that machine, maybe like 40, 50 years, if the chosen life from the lifetime for the manufacturer, we make those commutator segments so thick that even after maybe like 10, 20 years of long daily usage, they can still withstand, and the copper does not erode off. So that's why the commutator segments which are added over there, they are actually going to withstand it. Otherwise, the carbon brushes, yes, certainly they will be changed after every 6 months or 1 year, or depending upon how usage you are going to actually do them. So commutator and carbon brushes, very, very important. And actually the most decisive factor, as I told in the last lecture also, that carbon brushes and this LDI by DT effect, they are the two most notorious things for DC machines, and they are actually responsible for the DC machines being now obsolete and being taken over by the AC machine, and certainly the induction machine. Nowadays, almost 80 to 90% of machines in the industry have been replaced by induction machines. Coming on to the core losses, since we all know this is going to be made up of magnetic material, certainly, as I told you just above over there, all this is going to be a ferromagnetic material, this one, or even this one. So there are certainly going to be eddy current and hysteresis losses over there. They cannot be avoided over there. And we all know from the first chapter of Fitzgerald, another thing, that your hysteresis and eddy current losses, they are proportional to square of your magnetic field density, and they are also proportional to 1.5 times your the speed of your rotation, certainly over there, because if more speed is happening, this means that d phi by dt is going to be changing over there very fastly because of that dt in the denominator. So eddy current hysteresis losses, again dependent on your speed and your flux density. Then coming on to the mechanical losses. Mechanical losses, yes, it is happening for the carbon brushes and the commutator segment, but here this friction loss is not catering for that brush carbon brushes over there. This is actually catering for the air friction which is happening for these slots over there, because all this region over there is going to be filled with air. So there is certainly going to be some air friction involved. And then this shaft over there, which is actually going to go through all of this machine, it is going to be connected with some bearing. So that bearing is actually going to have some friction over there. So this friction over there, and then certainly the windage losses which are happening with the air over there. So this windage and friction losses, they are also proportional to the cube of your speed n over here. So these are also a very important factor. Normally, whenever in numerical you are going to solve, you are actually going to take them as some fixed value unless and until your speed changes from the full load speed to the no load speed. Otherwise, technically, mechanical losses have been given as lump sum value in any of the numericals or examples. Then the last thing, very much important in machines especially, but until and unless you go to your graduate studies or somewhere, these stray losses are normally written as something 1% of your full load losses over there. But so this is the normal term used in your book. So at this undergraduate level, what are those stray losses? Stray losses are those losses which cannot be accounted for. For example, a machine is going to be running for like 15, 20 years. So after some time, maybe it develops a loss in the shaft of your machine. The shaft is a little tilted, it's not center aligned, the air gap over here is not uniform from this air gap, or maybe there are some losses taking place inside the conductor, the resistance increases or something like that happens over there inside the windings. So all those losses, they are just taken as 1% of the full load losses for your machine. So stray losses are a very, very important factor, and they are taken over here. Now, based on all these losses which we discussed now, you have the power flow diagram. This is the power flow diagram of a generator, as you can see over there. And what we do in a generator, we have the mechanical power as an input, and you can see over here what is being applied. The torque applied is tau applied over there, APP as the subscript over there, and omega m is the speed of your turbine or the machine which is actually being applied. So this is the input power, and as soon as you apply this one, then you have some stray losses. Again, those stray losses are coming on for those bearing, any losses which cannot be accounted for. And then you have the mechanical losses taking place over there inside the machine, the friction and the windage, and then certainly the core losses, because at this point, after the core losses coming on, inside the armature. Now this has been converted into electrical power. From this was mechanical power, and then now it is converted to your mechanical power, or sorry, electrical power over here, P converted, and this is equal to EAIA, because EA is the induced EMF of your generator, IA is the current taking out from your armature through your carbon brushes, certainly to the load, and then this EAIA is going to pass through the resistance of the armature, that is I square R losses over there. Now technically speaking, this core loss should have been after this one. The reason of this one over here, it can be taken on this side also, but sometimes the I guess the book has taken in this way, that the core losses are happening inside the field winding also, and also the stator winding also, the armature winding also. So sometimes this can be taken on this side, or this can be taken on the other side. It's totally up to you. My vote is actually for on this side, because core losses, they are mostly happening inside the armature. So this should be after the conversion over there, because the flux and whatever, they are actually provided from the stator side, depending upon the type of your generator. So when you have passed on through your I square R losses, that is the field winding and the other thing, so you have your generator now giving an output over here as VTIL, and I guess I don't need to repeat over there the difference between VT. The VT was taken as the terminal voltage out from your generator, and for this was the terminal voltage out from your generator. And certainly if I'm talking about a generator, EA was equal to the induced EMF inside your generator, and for this one, your generator, and I don't need to tell that VT is certainly always smaller than EA. The reason, because EA is the total induced EMF over there, this one, and VT, so this after passing through the RA resistance of your machine, if it's a shunt generator, or even if it is a series generator, then it will be passing through RA and it will be passing through RD, that is the series field winding resistance. So this is a generator power flow diagram, and as if we come on to the motor over there, as you can see very carefully, that in a motor you have applied electrical energy, that is VT into IL. VT is again the terminal voltage, and I'm here talking about generically of a shunt motor. So IL over here can be called as total load current supplied by the supply, because this IL will be supplied to your IA and IF both over there. We will just discuss it later on just now. And then after passing through the I square R losses, because certainly there will be armature winding and field winding losses taking place inside the machine. So after this I square R losses, this is converted into mechanical. Now again, the same discussion or same point can be over here, that core losses should be here on this side, because core losses are happening, but core losses are happening after it is converted into flux. So that's why you can call it that this is the mechanical energy being produced over there. So this is the induced torque multiplied by, since we all know power is equal to tau omega, so this is the same equation, that EAIA, the induced EMF inside your generator, or sorry, your motor over here, because this now is the back EMF. Please remember, this is a motor, so this is actually the back EMF of your machine. So this back EMF multiplied by EA, and in this case, I don't need to actually tell over there that VT is certainly greater than EA, because this is a motor. You applied VT and you have a back EMF of smaller voltage over here. So this is certainly smaller after certainly the losses and all other losses taking place. And then when it is converted into your induced torque, you have the mechanical losses and you have the stray losses again happening, taking place, and the output now is the mechanical power as an output, and that mechanical power is the induced torque over here, certainly less than the induced torque. So I have T out over there, and this T out is certainly smaller than the induced torque, because some of the power is lost as mechanical losses, friction, windage, and stray losses on your bearings or any other late aging of your machine. So the motor over here, in this case, this is the power flow diagram of your motor, and in generator and motor you can see the power flow diagram is almost the same. You can argue on the core losses over there, but again with some arguments, please, whenever in an exam it is asked, please write down the arguments for your core losses to be added on which side. If you go with the book one also, no issues with that, but please write down the whole statement below it, just not only the diagram. Now, when you have the power flow diagram, you are going to talk on the efficiency. As I told you just before, that efficiency of a DC machine never above more than 60 to 70%. Our lab machines, the maximum efficiency I have measured on them is 64% or 65%, not more than this, because they don't have any compensating winding, interpoles, or any other remedial methods over there. It is a 4-pole machines. I asked you somewhere in the last lectures also that how many poles are there. I don't know how many of you have actually tried to find out. Our lab machines are all 4-pole machines with 1500 RPM as the rated speed of our motors and 1800 RPM as the generator rated speed over there. So the efficiency, the same formula, you already are familiar with this one. The efficiency is equal to P out divided by P in into 100. And if you don't have the output power, you can just calculate the losses from all those equations we just discussed above. So the efficiency is equal to P input minus P loss divided by P in multiplied by again 100. So this efficiency can be calculated over there. So over here, and your book, one thing, this was a little writing error, some misprinting error over there, and also there is some misprinting error on this formula also in your book. So please kindly correct it. Don't just cram the material and don't use your mind. Last topic for today is the shunt and separately excited motors. And coming on to that one, you have been doing this one in your lab. Now, if you see very closely, these two machines, they both are almost same to each other. Now, how same? The only difference these two have that in shunt motor, you have to apply a common supply, but in separately excited you have to supply two supplies over there. One is called as VT or VA, or actually the main supply voltage, because the main current is going to flow here, and VF is going to be having a little small voltage. As in our lab, it's just 150 or 200 milliamperes. So the only difference in these two is actually the use of two supplies over there. Here this is only one supply. So if I just mark these ones over here on my diagram, this current is going to be called as IL. This is actually the load current over there. The current which is going to flow inside my field winding is going to be called as IF, since this is going in the field winding, and this is IA. So I can easily call this one IL equal to IF plus IA. So the load current is equal to IF plus IA. And I guess this is EA. You already are familiar. This is the back EMF, because all three conditions of a generator phenomena are complete. So this back EMF will start to take place as soon as the motor starts rotating. So VT is going to be applying some voltage. Now, if we want to find out the motor equation for this one, we have to write down the KVL equation. And how to write down the KVL equation? KVL equation has to be written down for this last loop over there, the outside loop over there. So if I have this one over here as the equation, so if I want to write down the KVL equation, it's very simple over there. If I start supposedly from this side over there, I have minus VT, and then if I come back, I have this plus minus IARA, because the current is flowing from the positive side towards the negative side. So I am assuming the current is flowing in this direction. So this is plus IARA, and then this is plus EA, for obvious reasons, because this is the back EMF. By backward, because this is trying to oppose the applied voltage, because there is a generator phenomena taking place. But since the applied voltage is more, and since after the losses this generator phenomena is taking place, so the back EMF is always going to be smaller. So this EA is always going to be smaller than your VT, and then after EA this is going to be equal to 0. And if you rearrange this one, this is equal to VT equal to EA plus IARA. So this equation is the motor equation for your machine. That is the shunt motor over here, and very important equation, and all of the equations. Now, many of you can argue on this one that why we have not taken this central branch over there. Why? Because this current is very, very small as compared to the current which is flowing over here in the armature. And certainly this branch current is going to be just like 5 to 10% of the total load current. Why? Because this is an electromagnet over there. Now, if we do the similar kind of analysis over here for this kind of machine over here, this one is also going to have a field current, but this is totally being separated from another source, and this one is IA. So you can call over here IA is equal to IL. IF you can call it as here as VF divided by RF over there. Now, why this is so? Why I have not taken this inductance into effect? Because I am assuming this is a constant voltage source. And you all know whenever there is going to be a DC current flowing through an inductor, it behaves as a short circuit. So all this analysis which I am doing is at steady state analysis, not at the point when I'm actually having, maybe I have a small switch over there and I just turn on this switch over there, and then the switch is turned on. There will be some transients developed inside the inductor, just like you have been doing in your CAT course at the same time. So this is very important that your analysis, whatever this equation or all this, they are not taking into any inductance into equation. There's steady state analysis taking place over there. So again, if I want to try to find out the equation over here for the loop equation, the KVL loop equation, I have to take this into consideration, not this loop. Why? Because for obvious reasons, because this current is very, very small over here. So if you write down the equation, again, you can start it from here or here. Normally, we will take VT, you can take VA also, but since the applied voltage is taken as that terminal voltage, so this is going to be taken as minus VT, and then I have this plus sign, negative sign. So this will be plus IA RA plus EA equal to 0, because the loop is complete from here, because you are drawing the loop equation from over here. So this is equal to VT equal to EA plus IARA. So you can see now that the equation for the separately excited, as the word suggests, this is separately excited over here because it's separately excited from another supply. So the two equations for the shunt motor and the separately excited, they both are same over here. They don't have any difference over there. So what this means over here, that as soon as your load is going to be changing, they both are almost going to depict the same non-linear or linear analysis of characteristics in the load output. Now, when I'm talking about the load, these two machines are going to be discussed combinedly. So whatever analysis is done for a shunt motor is equally applicable on the separately excited motor. The only thing change over here is this, that here in this case, your IF is going to be divided by VT by RF. Here, this is going to be divided by VF by RF over here. Now, just a small analysis over there before I conclude this lecture over here is this, that when you are talking about a DC shunt motor or DC separately excited motor, so what happens over here, if I, let me just take this all and write it down over there on the next page. So I have this one, and I have this one over here. So now what happens if the machine is working? Now, if I take this relation over here and I have this relation over here, this is VT equal to EA plus IA RA over here. Now, if I just rearrange this equation is equal to VT minus EA divided by RA. Now, this equation is very much important and will be required in our analysis just now and also in the next lecture, lecture number 13. So overall, if you see very carefully in this one, what is IA? IA current is actually dependent upon the difference between VT and EA. So if the applied voltage is more, back EMF is less, resistance is constant, it's not changing. So this current will increase when this difference between VT and EA is going to be small. So when this difference is going to be small, your current IA will be small. If this difference is large, then this will be. So now supposedly your machine was working at a steady state point. So this is very important now. If your machine was working at a steady state point, what is the steady state point? Steady state point means that supposedly, just like take the lab example values, if the machine was working at supposedly 160 volt, your EA was supposedly equal to, at that point, equal to 155 volts. For example, I'm just taking some orthodox values over here. And your RA was supposedly equal to some 8 ohms value, just like you have been doing in the lab. So if you now do an analysis over there, at this point, what is happening? IA is equal to 160 minus 155 divided by 8 ohms. So this comes out to be something like 5 divided by 8. So this will be something like approximately, I guess, if I'm not wrong, this will be something like 0.6 something amperes over here. Correct me if I'm wrong anywhere. So over here, this 0.6 ampere current is flowing over there. This is a steady state point. The machine is working and it is giving out some RPMs over there. I'm not concerned with that RPM, whatever that value. Now, supposingly, this machine was doing some load over there, or maybe it was working at no load. Now, what happens? If this RPM, supposingly, was, for example, I'm just taking some orthodox value just to plug in some value so that you understand what I mean by that. Supposingly, the load was working at 800 RPM. Now I increase my load. Now increasing the load means that what will happen, the torque demand of my load is going to increase. So now when my torque demand of my load will increase, what will happen? The speed will decrease down. Why this will happen? Just to give you an analysis, if you're driving a car and there is a slight hike over there, and if you are supposedly going in third gear even, or like even second gear, and there is a torque demand now because the car has to climb on a steep ascent upwards, so what will happen? The speed will decrease down. Now when the speed will decrease down, now see this very carefully, this means that omega is also going to decrease down, because speed and omega, they are same things. One is in RPMs, other one is in radians per second. So what will happen now when omega has decreased down? This will actually change EA, which is equal to K phi omega. What is K? K is the machine constant. Phi is the flux being provided. And since the flux is dependent upon IF, so what will happen? These two will remain constant and there will be no change. Why? Because the applied voltage is still constant. It's 160 volt. The only thing changing over here is this omega is changing. It's decreasing. So what will happen now? That EA will decrease. Now when this EA will decrease, we all know just now, we just found out that IA was equal to VT minus EA divided by RA. So when this EA is decreasing, the rest of the two quantities, this VT and RA, they are still constants. So what will happen? Current IA will increase, and then current IA will increase. We know our induced torque formula was equal to K phi IA. We just proved it in the 2-3 lectures back. So when IA is increasing, your torque will increase, and it will continue to increase until your induced torque becomes equal to your load torque, which is actually the demand over there. Because the load on the machine was increased, the torque demand of the load was increased. So because of this, this equation will be satisfied. Then it will be working at a constant N, where this condition is being met. And certainly this N will be less than 800 RPM. Why? Because now the car is still going up, but it has to exert more torque. By more torque means it has to apply more energy, but the speed will be small. So just same thing you are experiencing in a car when you have trying to, I'm not talking about gears at present. Supposedly it's an automatic car and you're trying to go on a steep ascent forward, and supposedly the steep ascent is so small, the car will reduce its speed, but it will still apply that torque. So I guess this example over here is giving you an idea what is the difference between the torque and speed over there. So what has happened just now, that your speed, which was working at 800 RPM, it will decrease down. I'm not talking about any value over there. It may decrease to 700, 750, whatever. But this will work when the torque demand will be complete or equal. That is, the induced torque will be equal to T load, and this will be at a higher value of IA. So what will happen? Your IA will increase over here, and so the machine current will not be just 0.6. This may be like something 0.8, 0.9, or maybe even 1 plus amperes over there. So this means that the steady state analysis, the machine is working at a steady state point. As soon as you apply the load, the machine starts to take more current. More current means more torque, and more torque means that it's going to fulfill the demand of the load, but at a lower N speed, that is N, that is the RPM, or at a lower radians per second, that is omega over here. So I hope this is clear. So in the next lecture, now we are going to talk on the shunt motor or the DC separately excited motor. Remember, whatever analysis we do is equally applicable for both of these machines. The reason, they both have the same motor equation over here. So this is all for today. It's a very small lecture, nothing lengthy over here. So we have just talked about all this yoke effects, the power flow diagram, the losses, losses, the Bush voltage drop, the efficiency of DC machines, and in the last we have just talked about the shunt and separately excited motors over here. So I hope you've gone through this one. Thank you.